Hello, everyone. Welcome to Physics 212. This is lab 9, which is on the work energy theorem. So in this lab, I want to discuss the basic idea of work and how to compute work and what energy is, what kinetic energy is, what potential energy is. Now, the actual video that's going to follow is a video that I recorded during the pandemic. So the lab number doesn't match up. I believe I called it lab 5 in the video, but really right now you're doing lab 9. The questions that are in the following video are exactly the same as the questions that you have to answer from your lab manual. Okay, so if you go to the questions here, it's question 1, 2, 3, 4, 5, 6, 7, 8, and then I want you to also do 10, but not 9. I think in the following video, I called question 9 the same as question 10. But so the questions are exactly the same. And actually, because of the pandemic and there wasn't easy access to the lab manual, the questions are written out in detail as well. So they correspond exactly to what's in your lab manual. The other thing you'll notice is because it was during the pandemic, a lot of the data was collected for you. So you'll see tables filled in with some data, and then you just have to do a bunch of computations. So if you're watching this video right now because you missed a lab, you can either use that data that was given in those tables in the following video, or you can use your lab partner's data from this semester. It's all totally up to you. Okay, so with that in mind, we will switch over to the next video to cover all this information. Hello, everyone, and welcome to Physics 212. This is lab 5. So this lab is on the work energy theorem and conservation of mechanical energy. So I want to start by giving some definitions of what work is, how to compute it, what kinetic energy is, what potential energy is. So I'm going to give you the background so that we can do this particular lab. Okay, let me go to the iPad and start with a definition of work. Okay, so work is defined to be the mechanical transfer of energy from or to the environment into from the system by the pushes and pulls of external forces, okay? So it's a transfer of energy, think of it like from the environment to the system or to the environment from the system. And the way that we compute work depends on how many forces we have. So let me start with the work done by a single constant force. So work done by a single constant force. Okay, so let's say we have a situation where we have our object. Let's assume this is the single force acting on it, so a force F. And we'll say that the object undergoes a displacement in this direction. So it moves in that direction or undergoes a displacement of, say, delta R. We'll use delta X later, but delta R now is just a general way of saying the displacement. So it turns out that the work done only depends on the force that's parallel, the component of the force that's parallel to the displacement. So if I project this vector onto the displacement vector, then only this piece is going to be important. Right, so this is sort of like, think of it, I'll write it in general as just F parallel. So if this is my angle theta, right, that blue piece is F parallel. It's the component of the force that's parallel to the displacement. So the work done, I'll just call it W, by that force F is equal to the parallel component of that force times the displacement. Okay, and it turns out it's a scalar. Work is a scalar. It has no direction, just a magnitude, and the units are joules. Okay, but we know by looking at that diagram that to get that parallel component, it's simply going to be the magnitude of the force times cosine of that angle theta, right? So another way of writing this, I can say that the work done by that force F is equal to the magnitude of F times, I'll write delta R first, and then times cosine of the angle theta. And again, it'll be in joules. This should be a J here. So this will be in joules. All right, so that's the definition of work, right? F times displacement times the cosine of the angle. And the angle is always between the force, so between the force vector and the displacement vector. That's the angle theta. What if we have multiple forces acting on the object? So what's the work done by multiple forces? So work done by multiple, and we'll assume they're constant forces. So multiple constant forces. So let's say I have my object. Let's assume that I have three forces acting. So I have, let's say F1, maybe F2 is like this. And then let's say F3 is like that. And let's say the object undergoes a displacement in this direction, called delta R. And I want to know the work done, the net work done by all three of those particular forces that's acting on the system. Well, there's a couple ways you could do this, right? You could find the net force first. So if you add those three vectors together, like if we did a simple, tip to tail, if I start with F1, let's say I add F2, something like this. So this is F1, this is F2, and then F3 is going to be like that. Then we know that the net force, the sum of those, is going to be a vector that goes from the tail of F1 to the tip of F3, right? So it's going to be like this. This is like F net. So one way of calculating the net work, right, the work done by the net force, is to calculate the net force, which we just did, and then we can simply use the fact now that you can think of the net force acting on the object by itself. Remember, it's undergoing this displacement. If we assume we know the angle between the net force and the displacement vector, then the net work, so the work done by the net force, is simply going to be the net force times the displacement times cosine of theta. So in other words, you can treat the net force as your single force, right? Because now it's just like a single force. So that's one way of finding the net work done on the object. Another way, which is maybe even better in some sense, is finding the work done by each of those forces individually. In other words, I want to calculate, say, the work done just due to F1. So remember, that's going to be F1 times delta R times cosine, I'll call it of theta 1. And theta 1 is the angle between F1 and your displacement vector. Then I would calculate the work done by just F2. Then calculate the work done just by F3. And it turns out that the net work done is simply going to be the sum of those individual works. So this will be the work done by F1 plus the work done by F2 plus the work done by F3. So since it's a scalar, you can simply add those values together, and that will give us the net work. Okay, so each of these, I didn't write this out, but this of course is just going to be F2 times delta R times cosine of the angle, but now the angle is the angle between F2 and delta R, right? And then F3 delta R cosine, I'll call it theta 3. That's the angle between F3 and delta R. So if we go back to this picture, right, this would be theta 1. This would be theta 2 from there to there. And then I'll do another color green. This will be theta 3. Okay, so you calculate each individual work, add them together, and that's going to be the net work done. Okay, a couple of definitions I want to remind you guys of, and you probably have seen all this in lecture by now, but let me just remind you. There's some energy definitions that we're going to need. So the first one is the kinetic energy. This is really the translational kinetic energy. We're not going to talk about rotation yet, so just translational kinetic energy. And it's energy due to the motion of the object. So energy due to the motion of the object. And how do we compute it? Well, typically we call it K, or sometimes in lab manual or my lab handouts, I'll use KE. They both mean the same thing, kinetic energy. And it's simply 1/2 times the mass of the object times its translational velocity squared. So times its whatever its velocity is at that instant squared. Okay, so we will need that. Also, the other type of energy we'll need is something called the gravitational potential energy. And this is really the energy due to the interaction between like two objects. However, it's easier to think about this as it being just the energy due to the position of an object in a gravitational field. It's kind of a simple explanation, but you guys will learn, get into more detail in lecture. For now, I just want to keep it simple. So in terms of the equation, sometimes you'll see this written as like U for potential energy, and in particular, we want gravitational, so there's like a sub G there. Or often in my handouts, I'll just use PE. So they both mean gravitational potential energy. And it's simply equal to the mass times the acceleration due to gravity times the vertical distance. Y is like the vertical distance above some reference point. So this is the vertical distance above, or it could be below too, but usually say above some reference point. So there's some reference point where you assume the potential energy is 0, right? So the Y would be 0, and you measure from that particular reference point. It turns out that the actual potential energy doesn't really matter. We're really only interested in the change in potential energy. So it doesn't matter where you choose your reference to be. Okay, so now what I want to do is I want to explain the work energy theorem, but I want to do it in the most general way possible. So let me write this out. This is like think of this as like the general work energy theorem. So what this says is that the net work done on some particular system, it's equal to the change in energy of that system. But the change in energy could consist of many different types of energy. So it could be, so the change in energy could equal to the change in kinetic energy plus the change in gravitational potential energy. And those are really the ones that we're going to worry about in this particular lab. But then later, you may, in more physics that you see later, you might see change in elastic potential energy, right? So if you have a spring in the system, if there's any friction, you could have a change in thermal energy. So TH is thermal. There could be maybe a change in chemical energy plus dot, dot, dot. And you can keep adding different terms, right? In most cases, we're going to assume that most of those terms are 0 for lab, but change in energy consists of all those changes. And there's many, many different types of energy. Okay, so in the first part of the lab, let me go back to the handout. So in part 1 of the lab, basically what we're going to have is a cart, which is on the air track. So here's the cart. It's on an inclined air track. It starts at rest, right, at some initial position, and it's going to accelerate. We're going to release it from rest. It's going to accelerate down the air track, and eventually it'll pass this final position, and it will have undergone a displacement along the track of 1 meter, right? 100 centimeters, which is 1 meter. And ultimately what we want to do is we want to calculate the work done by the net force on that cart as it goes down the track. So the net work done as it undergoes that displacement of 1 meter down the track. Okay, so first of all, make sure you watch my short video there where I show you the actual equipment and how I collected the data. It's hard to see sometimes just from a picture here. But the first thing I need to do to figure out here is I need to figure out the net force acting on this cart. So let me go back to the iPad to do that. Okay, so in this part, so this is just basically part 1. We have the air track, it's on an incline, so something like that. It makes an angle, let's say theta, with the horizontal. And we have this cart, which is on the track. And so the first question is, what are the forces acting on the cart, right? And actually there's 2 forces. We have the weight, right? The gravitational force, which always acts towards the center of the earth. So that's going to act straight down. That's the weight. And then we have a normal force that the air track exerts on the cart, and it's always perpendicular to the surface. So perpendicular to the air track. So that's going to be up like this. So that'll be our normal force. And in this case, our system, and this is really, it's a subtle point, but this is really important. Our system is just going to consist of the cart. So the system is just a cart in this case. So if we go to that equation for the net work done, remember the net work done is equal to the change in kinetic energy plus the change in gravitational potential plus the change in elastic potential plus the change in thermal, etc. Well, it turns out if our system just consists of the cart, then since it doesn't consist of the Earth, there's no like change in potential energy. There's no spring in there, so there's no change in elastic energy. We're assuming that it's frictionless because it's on the air track. So it turns out that basically all of these terms here, we're going to set equal to 0. And then we can say that the net work done, so the work done by the net force, or the sum of all the works done by all the forces, is simply equal to the change in kinetic energy. And actually, this is what most books call the work energy theorem. The one I use, I call sort of the general work energy theorem. It's a little more inclusive. Okay, so what is the net work done on this cart? Well, let's think about this. If I create a little coordinate system, let's say X is traveling, or X is along the air track, so something like that, and then Y will be perpendicular to it. Then first thing I can do, I can find the components of the weight, right? I can project the weight vector onto the y-axis, and this will be the y component of the weight. This will be wy. I can project it onto the x-axis. So this will be wx. This is my angle theta right here. So it turns out that if you think about this, that the net force acting on that cart is simply going to be the x component of the weight, right? So the normal force and the y component of the weight, those are going to add to 0, right? They're going to cancel out. They're going to add to 0. So the only piece that's left is the x component of the weight that's accelerating the cart down the air track. So the net force is simply equal to the x component of the weight. And we know that this cart is undergoing a displacement down the air track, right? In fact, if you want, you can call this like delta x now. Instead of delta r, we'll call it delta x. So using the work energy theorem, right, I know that the net work is equal to, in this case, the change in kinetic energy. Well, the net work is going to be the net force times the displacement times cosine of the angle. But remember what the angle is. The angle is between the net force and the displacement vectors. In this case, they're both in the same direction. So that angle is 0 degrees. So really this is going to be just equal to 1. And that's got to equal change in kinetic energy. Okay, so in this case, right, this will be Wx delta x cosine of 0 degrees. And then I can write this out as 1/2 mv final squared, all right, v final in the x direction squared, minus 1/2 mv initial in the x direction squared. So it's the final kinetic energy minus the initial kinetic energy, right? Change in kinetic energy. And we already know that this is equal to 1. I can simplify this some more, right? Wx is simply going to be, if you look at the picture here, right? This is Wx, so it's opposite the angle. So it turns out Wx is going to be mg sine of theta. So this is just mg sine theta delta x, and that equals 1/2 mv final in the x squared minus 1/2 mv initial in the x squared. Okay, then we can also say, and we did this in one of our previous labs when we looked at the acceleration of a cart down the inclined track. We can also find sine of theta, right? So if you look at the track itself, remember sine of theta, if we know the initial height and the final height of that cart as it travels that 1 meter down the track, then sine of theta is simply equal to the initial height minus the final height divided by the displacement. So if I substitute this value in for sine theta here, so this will be mg, now I have height initial minus height final over delta x, but then I multiply by delta x, and it's again equal to the change in kinetic energy. Turns out the delta x's cancel, right? Another simplification is we know that the cart is starting at rest, right, for our experiment. So I know that v initial in the x is 0, right, meters per second. So this term is gone. So that simplifies things. And ultimately what I want to do is I want to solve for the final velocity. I want to solve for v final in the x direction. Okay, so it's a little more algebra, right? So right now I have mg times h initial minus h final is equal to 1/2 m v final in the x squared. You could cancel out m's, right? Multiply both sides by 2. So on this side, the 2 will cancel with the 2 in the denominator, right, of the half. So these cancel. And then finally take the square root of both sides. So we're going to find that v final x is equal to the square root of 2g times h initial minus h final. Okay, and we're gonna call this our predicted velocity because it's predicted using the work energy theorem. Right, so really the goal of this first part of the lab is to compare the predicted final velocity with an experimental final velocity. So this is the predicted one, again, predicted from the work energy theorem. Okay, what's the other way that we can find the final velocity? And again, it'll be sort of our experimental one, the second way. So remember, we actually did this before too, when we looked at the acceleration of the cart just down the air track in lab, I think it was lab 2. So we can find the final x using kinematics. Okay, how do we do that? Well, the first thing, and this is really important, the cart is undergoing a constant acceleration as it goes down the air track. How do we know that? We could actually just use Newton's second law, right? We could say that the sum of the forces in the x direction, which is, remember, down the track, is equal to max. Well, the only force acting in the x direction is the x component of the weight, so that equals max. But the x component of the weight was mg sine theta. That's equal to max. And then if I cancel the m's here, I find that the acceleration is g sine theta. But theta is constant, right? Because that angle is not changing. It's the same constant angle that the track makes with the horizontal. And g, of course, is a constant. So the acceleration is a constant. So we know that acceleration is a constant. Okay, well, now what we can do is we can actually compute the average velocity 2 different ways. And again, this is exactly the same thing we did in lab 2. I can say that the average velocity is equal to delta x over delta t. That's the definition, right? It's a displacement divided by the time. Or because I know that the acceleration is constant, I can also say that the average velocity is equal to the average of the initial and final velocity. So I can add them and divide by 2. That's only true if the acceleration is constant, but we know it's constant in this case. Then if I set these equal, because they both represent average velocity, so if I set them equal, and then I can make one more simplification. Remember that the cart is starting at rest, so v initial in the x is 0. So therefore, v final in the x, which we're going to call our experimental final velocity, is simply equal to twice the average velocity, right? Twice delta x over delta t. Okay, and again, it's because the acceleration is constant and we're starting the cart at rest. Then the final velocity is always going to be twice the average velocity. Okay, so in terms of this part of the lab, let's go back to the handout and go over what questions you guys need to answer. So I drew some pictures here and you can see, right, if you add the normal force plus this is the weight vector. So if I go from the tail of the normal force to the tip of the weight vector, I get this resultant force, which is my net force, but that's just equal to the x component of the weight. So that's why we're saying that the net force is simply the x component of the weight. So we just did this on the iPad, right? We derived the fact that the final velocity in the x direction after it goes that 1 meter must be equal to the square root of 2g times the change in the height. And think of this as your predicted final velocity. And then by using kinematics, right, and knowing that the acceleration is constant and the cart is starting at rest, we also found that the final velocity, think of this as v final in the x direction experimental, that's equal to twice the average velocity, right? 2 times delta x over delta t. Okay, so for the experiment, again, make sure you watch the video so you can see exactly how I got all this data. So the first table here is I just got the time it took that cart to travel the 1 meter down the air track. So it started at rest and traveled 1 meter, and this delta t is the time. So I did 10 trials and I measured that time that it took to travel down the air track 1 meter. So question 1, I want you to compute the average time and make sure you round it to 4 decimal places. And now compute the experimental final velocity, which we derived that formula earlier. Remember, it's twice delta x over delta t. But we know in this case that delta x is simply going to be 1, right? Because it travels 1 meter down. The displacement is 1 meter down the air track. Okay, and make sure you show me that calculation. Then I measured the height at the highest point, which I'm calling h initial in this case, and at the lowest point, h final, right? So these are the heights in meters. So now we can calculate the final velocity as predicted by the work energy theorem. So that was this formula. Fill in the table here, right? So predicted, again, is from question 2, experimental is from question 1, and then compare them by computing the usual percent experimental error. Make sure that you show me that calculation for the percent error. Okay, question 4. How much work is done by the normal force when the cart undergoes the 1 meter displacement down the track? So again, you guys may know this already from lecture. So think about that, right? The normal force and the displacement vector, those make an angle relative to one another of 90 degrees, right? They're right angles to one another. So that should help you answer that question. So how much work is done just by the normal force when it goes down the 1 meter down the air track? Question 5. Now I want you to compute the work done by the net force, right, while it undergoes the 1 meter displacement. So remember, the net work is going to be the net force times delta x times cosine of the angle. But in this case, the net force was just the x component of the weight. The displacement is delta x, and it was cosine of 0. So I don't even have cosine in here. It's times 1, right? Cosine of 0 is 1. So it's simply going to be mg sine theta times delta x. And instead of trying to figure out the angle, right, it's too hard to measure the angle. We can just use the fact that sine theta is h initial minus h final over delta x. Okay, so you should be able to from that, you should be able to compute the net work, right? That'll be in joules. Then question 6, how much kinetic energy does the cart have at the initial position? Remember, the cart is starting at rest, okay? So then you want to explain that. Question 7, compute the kinetic energy of the cart at the final position. So we just use the formula for kinetic energy, 1/2 mv squared, where the velocity, the final velocity, just use the one from question 1, your experimental final velocity from question 1 when you do this computation. Okay, use the results from question 6 and 7 to compute the change in kinetic energy. Remember, change is final kinetic energy minus initial kinetic energy, right? We computed the final kinetic energy in question 7, and basically we computed it in question 6, the initial kinetic energy in question 6. You have to explain why it's that particular value. And then finally, once after you've done that, right, so you can write the answer here, the change in kinetic energy. Compare this answer to the work done by the net force from question 5. And what should be true about those two values, the change in kinetic energy and the work done by the net force, right? The net work done. Okay, question 9, I want you to think about a little bit. So it says, the work done by the net force acting on the cart is always equal to the change in kinetic energy. So that's true. Can it be true that the work done by one of the individual forces alone will be greater than the change in kinetic energy? And my hint is, well, what if you have like multiple forces acting? What if there was like a frictional force acting, against, so it's like resisting the motion, and then you have several forces that are accelerating the cart in the opposite direction, right, of the friction. So can there be the work done by one particular force? Can it be greater than the change in kinetic energy?